Exception 5 in 310.15b2 of the National Electrical Code states that adjustment factors shall not apply to medium voltage cable without an overall outer jacket. Understanding this exception requires delving into the purpose of ampacity adjustment factors and the typical applications of medium voltage cables. Ampacity, in electrical terms, is the current, in amps, that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. The National Electrical Code provides tables that list the ampacities of various conductors based on their size, insulation type, and temperature rating. These tables assume specific conditions, such as an ambient temperature of 30 degrees Celsius, which is 86 degrees Fahrenheit, and no more than 3 current-carrying conductors in a raceway or cable. However, real-world installations often deviate from these ideal conditions. Firstly, ambient temperature can be higher than 30 degrees Celsius, especially in industrial environments or in areas with high sun exposure. Higher temperatures reduce the ability of the conductor to dissipate heat, which can lead to overheating and insulation degradation. Secondly, when multiple current-carrying conductors are bundled together in a raceway or cable, the heat generated by each conductor can raise the temperature of the other conductors. This mutual heating effect also reduces the ampacity of each conductor. To account for these deviations, the National Electrical Code requires the use of adjustment factors. These factors are multipliers that are applied to the ampacity listed in the tables to correct for ambient temperature and the number of current-carrying conductors. For example, if the ambient temperature is higher than 30 degrees Celsius, the temperature correction factor is applied to reduce the ampacity. Similarly, if there are more than 3 current-carrying conductors in a raceway, a conductor grouping factor is applied to reduce the ampacity. These adjustment factors ensure that the conductors do not exceed their temperature rating under the actual conditions of use. Now let's consider medium voltage cables. Medium voltage cables are typically used for power distribution in industrial facilities, commercial buildings, and utility systems. They operate at voltages ranging from 2400 volts to 35,000 volts, depending on the specific application and regional standards. Medium voltage cables are designed to withstand these high voltages and to provide reliable power distribution. There are several types of medium voltage cables available, each with its own characteristics and applications. Some common types include shielded power cables, which have a metallic shield to contain electromagnetic fields and to provide a path for fault current, and non-shielded power cables, which do not have a metallic shield. Medium voltage cables can also be classified based on their insulation material, such as cross-linked polyethylene, ethylene propylene rubber, and other types of insulation. Exception 5 in 310.15b2 specifically addresses medium voltage cables that do not have an overall outer jacket. An overall outer jacket is a protective layer that covers the entire cable assembly, including the conductors, insulation, and any shielding. The jacket provides mechanical protection, environmental protection, and electrical insulation. It helps to protect the cable from abrasion, moisture, chemicals, and other factors that can damage the cable. The National Electrical Code recognizes that medium voltage cables without an overall outer jacket are typically installed in different types of applications than cables with an overall outer jacket. Medium voltage cables without an overall outer jacket are often used in open-air installations, such as overhead power lines or in direct burial applications, where the cable is buried directly in the ground. In these applications, the cable is exposed to the environment and is not enclosed in a conduit or raceway. The exception states that adjustment factors shall not apply to medium voltage cables without an overall outer jacket. This means that the ampacity of these cables is not reduced to account for ambient temperature or the number of current-carrying conductors. The reason for this exception is that the adjustment factors are based on the assumption that the cables are installed in a closed conduit or raceway. In a closed conduit or raceway, the heat generated by the conductors is trapped inside the enclosure, which can raise the temperature of the conductors and reduce their ampacity. However, in open-air or direct burial applications, the heat generated by the conductors can dissipate more easily into the surrounding environment. This means that the temperature of the conductors is less likely to be affected by ambient temperature or the number of current-carrying conductors. Therefore, the adjustment factors are not necessary for medium voltage cables without an overall outer jacket. It is important to note that this exception only applies to medium voltage cables that do not have an overall outer jacket. If the cable has an overall outer jacket, the adjustment factors must be applied to the ampacity of the cable. The National Electrical Code provides detailed information on how to calculate the adjustment factors for different types of cables and installation conditions. The exception in 310.15b2 acknowledges that medium voltage cables lacking an overall jacket often find use in scenarios where heat dissipation is more efficient, negating the need for typical ampacity adjustments based on conduit or raceway assumptions. This is particularly relevant in open-air installations or direct burial scenarios. The absence of an outer jacket implies a different thermal environment compared to jacketed cables in enclosed raceways. When cables are installed in conduit or raceways, the surrounding enclosure inhibits heat dissipation. The heat generated by the conductors becomes trapped, leading to a temperature increase within the enclosure. This elevated temperature affects the cable's ampacity, necessitating the application of adjustment factors as outlined in the National Electrical Code. These adjustment factors account for the reduced heat dissipation capability and ensure that the conductors operate within their rated temperature limits. However, when medium voltage cables are installed without an overall outer jacket in open air or direct burial applications, the surrounding environment allows for more effective heat dissipation. In open air, the cable's surface is directly exposed to the ambient air, facilitating convective cooling. The heat generated by the conductors is readily carried away by the moving air, preventing a significant temperature buildup within the cable. Direct burial also offers improved heat dissipation compared to enclosed raceways. The surrounding soil acts as a heat sink, drawing heat away from the cable and maintaining a lower operating temperature. The effectiveness of heat dissipation in direct burial depends on factors such as soil type, moisture content, and burial depth. Soils with higher thermal conductivity and moisture content tend to dissipate heat more effectively. The National Electrical Code recognizes these differences in thermal environments and provides specific guidelines for ampacity calculations based on installation methods. The exception in 310.15b2 is not a blanket exemption from all ampacity considerations. While adjustment factors for ambient temperature and conductor bundling may not be required, other factors such as earth temperature in direct burial applications may still need to be considered. The National Electrical Code provides tables and formulas for determining the appropriate ampacity for various cable types and installation conditions. These resources should be consulted to ensure that the cables are operated within their rated limits. It's crucial to understand the underlying principles behind the exception in 310.15b2. The exception is not an invitation to disregard ampacity considerations altogether. Instead, it acknowledges that the thermal environment for medium voltage cables without an overall outer jacket is often different from that of jacketed cables in enclosed raceways. By understanding these differences, electrical engineers and installers can make informed decisions about cable selection and installation methods. The absence of an outer jacket doesn't automatically guarantee that ampacity adjustments are unnecessary. The specific installation conditions must be carefully evaluated to determine the appropriate ampacity for the cable. Factors such as ambient temperature, soil thermal conductivity, and burial depth can all influence the cable's operating temperature. In some cases, it may still be necessary to apply adjustment factors to account for these conditions. The National Electrical Code provides guidance on how to determine the appropriate adjustment factors for various installation scenarios. It's important to consult these resources to ensure that the cables are operated within their rated limits. Another important consideration is the type of insulation used in the medium voltage cable. Different insulation materials have different temperature ratings and heat dissipation characteristics. Cables with higher temperature ratings can operate at higher temperatures without degrading. The National Electrical Code specifies the maximum allowable operating temperatures for various insulation types. When selecting medium voltage cables without an overall outer jacket, it's important to choose cables with insulation that is appropriate for the intended application. In high-temperature environments, cables with high-temperature insulation should be used to ensure that the cables can operate safely and reliably. The exception in 310.15b2 is not intended to encourage the use of medium-voltage cables without an overall outer jacket in all applications. The decision to use these cables should be based on a careful evaluation of the specific installation conditions. In some cases, it may be more appropriate to use jacketed cables in enclosed raceways. Jacketed cables provide additional mechanical protection and environmental protection, which can be beneficial in certain applications. The choice between jacketed and unjacketed cables should be based on a comprehensive assessment of the risks and benefits of each option. It's also important to consider the long-term reliability of the medium voltage cables. Cables without an overall outer jacket may be more susceptible to damage from abrasion, moisture, and chemicals. In harsh environments, it may be necessary to take additional precautions to protect the cables from these factors. These precautions may include using protective coatings, providing physical barriers, or implementing regular inspection and maintenance programs. The overall goal is to ensure that the medium voltage cables operate safely and reliably for their intended lifespan. In summary, Exception 5 in 310.15b2 of the National Electrical Code states that adjustment factors shall not apply to medium voltage cables without an overall outer jacket. This exception is based on the understanding that these cables are typically installed in open air or direct burial applications where heat dissipation is more efficient. However, it's important to carefully evaluate the specific installation conditions to determine the appropriate ampacity for the cable. Factors such as ambient temperature, soil thermal conductivity, insulation type, and long-term reliability should all be considered. The decision to use medium voltage cables without an overall outer jacket should be based on a comprehensive assessment of the risks and benefits of each option. This exception should not be interpreted as a blanket exemption from all ampacity considerations, but rather as an acknowledgement of the different thermal environments in which these cables are typically installed. Ultimately, the goal is to ensure that the medium voltage cables operate safely and reliably for their intended lifespan. Remember to always consult the latest edition of the National Electrical Code and to seek the advice of a qualified electrical engineer when designing and installing electrical systems. The National Electrical Code is a complex document, and it's important to have a thorough understanding of its requirements. A qualified electrical engineer can provide valuable assistance in ensuring that electrical systems are designed and installed in accordance with the code.